We're in Rosen, Discrete Mathematics and its Application, Chapter 1.4 on predicate logic and propositional functions. We've been discussing quantifiers, and I want to spend some time in practical application talking about how we can translate sentences uh, that contain quantifier language into symbolic propositional functions bound by quantifiers. All right, here's our first example. Translate the following sentence. Every student in this class has taken a course in Java. So here's a word that suggests a quantifier we want to include. And then there's an implied, or there's a connoted implication in here that if the student is in this class, then the student has taken a course in Java. So if then. So we have a quantifier for every quantifier and some implication language. All right, so the other thing we have to do is decide what the domain is, because that will determine how we structure the propositions to translate the sentence. So if I select students in the class as the domain, and then I denote j of x as the propositional function x has taken a course in Java, then for every x, j of x correctly translates our sentence. We don't even have to worry about whether the student is in this class or the implication, because we're only considering students in the class. On the other hand, if we decide, or perhaps are told, that the domain is all people, then for every x, j of x won't work, because we aren't saying that every person has taken Java above. What we are saying is that for every person, if they're in the class, then they've taken Java. And so that would be written out as for every x, s of x implies j of x. And that's how we translate that for the domain being of all people. One erroneous way to state it would be like this: for every x, s of x, and j of x. Well, that's not true, and why? Well, this statement says that every person is in the class and has taken Java. And the sentence doesn't try to state that every person in the world is in the class. It just says if they're in the class, then they've taken a course in Java. Let's look at another one. All right, now it's some student in the class has taken Java. So we'll identify the quantifying language there. And what is happening is we have a student in the class and a student that's taken Java. So we'll have two propositional functions related to that, as we saw before. Again, we have to decide on the domain U, and then the first case, if it is all students, if it's only students in the class, then we can just write for every, there exists x, j of x as a translation of that. On the other hand, if you use all people, then we will translate it as there exists x such that they're in the class and that they've taken Java. There's at least one person who's in the class and has taken Java. It's possible that everybody in the class has taken Java, or only one, but it is not possible that there are people in the class that have not taken Java, given our statement above. Now, earlier we had seen implication language buried in there, but we don't see it here, and the reason has to do with the quantifier. Let me show you. If we were to state that there exists x such that s of x implies j of x, that would not be a correct translation of our sentence. And think about why that might be, considering the vacuous case of the implication. Remember, this translation must be true whenever the sentence above is true. But it is possible that S of x implies J of x is a true statement even if nobody in the class has taken Java. Um, because what if somebody is not in the class? If somebody's not in the class, then the hypothesis will be false, and whatever the hypothesis is false, you get a true statement. So this would not be, I should say equivalent. This would not be a correct statement because of the vacuous case. So one rule of thumb is be very careful, and very rarely will you ever use the implication and the existential quantifier. All right, returning to the Socrates example, we're going to state that in terms of quantifiers. But first we have to introduce some propositional functions. Man X says X is a man, and mortal X says X is mortal. And then our domain will be all things. All right, so we had said that if all men are mortal, so that would be all men, all basically for every person, if they're a man, then they're mortal, and that's what we state here. And then we have a function, like we said earlier, that tells whether somebody is a man. And Socrates is a man, can be stated as man at Socrates. So we want to conclude then that mortal at Socrates is a true statement. We still can't do that yet, but we have the tools for writing those two, actually these three propositions down symbolically. And we'll learn later how to do that.